Good afternoon, everyone. Now it's 2 o'clock in the afternoon in Taiwan. And we are very happy today to have Professor Atsushi Kumamoto of the Tohoku University to give us an online lecture. He has given us a very brief CV, but however, it contains a lot of information. That is, he graduated from, got his PhD from Tohoku University in 2000. But since graduation, he has done a lot of work. Because he's a very experienced instrumentalist, especially in plasma waves measurements. So today's talk, the title is the measurement of electron number density and plasma waves in rock experiments. He has participated in a number of rocket experiments and still doing a lot of rocket experiments. And I think that he will tell us more about it. On the other hand, he has joined quite a number of space missions, like the Earth mission, which is a very important mission to study the inner mesosphere of the Earth. And then he has also participated in Kakuya, right? Kakuya, for to the moon, and then also on the Nozomi to Mars, and also on the Akebono mission on the plasma wave sensor. So I think that he must be one of the leading experts now, in the world. So we're very happy to have him giving us a talk. Professor Kumamoto, please take it away. Thank you so much.
Thank you, Professor Ip. I'm Atsushi Kumamoto from Tohoku University, and thank you very much for invitation to this seminar as a speaker. In the beginning of the today's talk, let me introduce myself briefly. As Professor Ip kindly introduced for me. I was working on the development, operation, and data analysis of plasma wave receiver and radar sounder of magnetospheric orbiter and lunar orbiter and several ionospheric sounding rockets. So my research interest is mainly on the plasma physics in the ionosphere and the magnetosphere based on the observation and lunar geology and lunar science based on the subsurface radar sounding. And I'm also working on the investigation for proposal for subsurface radar sounding of the Moon, Mars, asteroid, and comets in future missions. And this is the outline of today's talk. First, I would like to show some results from electron number. Then, in this talk, I would like to focus on the electron number density and plasma wave observations performed in the ionospheric sounding rocket experiment. So the first topic is on the some results from electron number density and plasma wave observation performed in the previous ionospheric sounding rocket experiment. Then I would like to explain how NEI measures the electron number density, because I think the impedance probe is not so familiar to you. And finally, I'd like to introduce, I'd like to show our plans for future missions. And then let's move to the first topic. In the previous ionospheric sounding rocket experiments, we used impedance probe called NEI for measurement of the electron number density. And this photo shows this photo shows electric circuit unit of the NEI, NEIE, and sensor unit, NEIS. And beryllium copper metal ribbon is winded in this NEIS. And after the launch of the rocket, the cap of the NEIS is removed, and beryllium copper ribbon is deployed by its elasticity with forming cylindrical metal probe like this. And this is used for the probe for measurement of the electron number density. The length of the probe is 1.2 meter. And NEI measures the capacitance of the probe extended in the plasma in a frequency range from 0.1 megahertz to 20 megahertz. And this probe capacitance and this is probe capacitance obtained by the ionospheric sounding rocket SS 5203 experiments. And since it is known that probe capacitance becomes minimum at upper hybrid resonance frequency here, and we can determine upper hybrid resonance frequency of the plasma expressed by this equation, and we can derive plasma frequency expressed by this equation, and we can also derive electron number density NE. And these are vertical profiles of electron number density in the ascent path and descent path. We can see density increase around the altitude of 300 kilometers. These are ionospheric F region, and in addition, we can see some irregularity of the plasma, probably due to the precipitating auroral electrons, because this rocket is launched in the dayside auroral region in order to perform the measurements for the phenomena of ion outflow in order to perform the observation. of the ion outflow in the day-side cusp region of the magnetosphere. And these are vertical profiles of electron number density obtained by 4 ionospheric sounding rockets. NEI is installed on several ionospheric sounding rockets launched from Kagoshima Space Center in Japan. And these are vertical profiles obtained by those ionospheric sounding rockets. And you can see the increase of the electron number density due to the bottom side of the ionospheric F region around here, around 300 kilometers. And in addition to this F region increase, in addition to the increase due to the F region, bottom side F region, you can see thin, dense plasma layers here at altitude about 100 kilometers. These are ES layers, sporadic E layers. And sporadic E layer is known as the known to cause unusual radio reflection at altitude of 100 kilometers and also cause crosstalk in radio communication and broadcasting. And this is ES layers observed by the ionization on the ground. We can see dense ES layer appeared at local time of 17 and disappeared. And this ES layer is ES layer disappeared just after the 30 minutes later, like this. And formation of the ES layer is explained by wind shear theory. If there are shear of the neutral wind in the ionosphere like this, dragged ions along the magnetic field obtained vertical velocity to be concentrated at the some altitude. In addition to the neutral wind shear, it is also suggested that the electric field also affected the formation of ES layer. And this, the verification of the wind shear theory was tried in sixth campaign. And in sixth campaign, two split ES layer were observed by NEI installed on 2 rockets. And in this campaign, in addition to the electron number density, electric field was measured by dipole antenna, and wind velocity was measured by the trimethyl aluminum release from the rocket. Trimethyl aluminum produces a luminous cloud, and they are dragged by the neutral wind. And by ground-based observation, we can determine the velocity of the neutral wind. And by using this equation, we can estimate vertical velocity of the ions by using this equation. And in addition, we can consider that plasma plasma concentration could be produced by plasma concentration could be could occur at altitude range where the BZ gradient of the negative gradient of negative gradient of BZ vertical profile in BZ vertical profile. And so, by using this equation and we can obtain BZ vertical profile. We can see negative gradient here and here. And ES1 layer is so the ES1 layer can be explained by this negative gradient at this altitude range by using this equation. So ES1 layer can be explained by wind shears. But but on the other hand, we cannot find negative gradient for ES2 layer. So this model, considering only the neutral wind shear, is not enough for interpretation of this phenomena. So in the lower panel, by using this equation, including electric field, we also can obtain another BZ vertical profile by including E-field effect. And obtained another in this BZ profile, including E-field, we can see negative field, negative gradient of BZ vertical profile for ES2 layer. We can see negative gradient for ES2 layer. ES2 layer from this analysis, the E-field contribution is E-field can be contributed for formation of ES2 layer. This is the result of the verification of wind shear theory in sixth campaign. To summarize for this analysis result, ES1 is formed by the wind shear, and ES2 is not ES2 is formed not only by wind shear but also the electric field contribution. ES2 is formed EMS. This two split ES2 layer can be formed by contribution of the electric field. It is suggested. It was suggested by the analysis performed in sixth campaign. And in addition to NEI, plasma wave receiver called PWM was also used in several ionospheric sounding rocket experiments. In SS 520 sounding rocket experiments, the PWM is installed as a subcomponent of NEI. So the instrument name is NEI/PWME. And the frequency range, observation frequency range of PWM is from 0.3 kilohertz to 22 megahertz. And the interval of the sweep start is 125 millisecond, less than 1 second. Less than 1 second. And antenna unit of is the antenna of another instrument. Electric field detector was used for the PWM antenna, and they are made of CFRP, and the length of the antenna was 3 meters. And this is example of the observation result of the plasma and radio wave observation performed in SS523 sounding rocket experiments. And this rocket was launched in the Dayside auroral region, and the highest altitude of the sounding rocket was reached to 700 kilometers. The various plasma waves and radio waves can be received. We can see auroral hiss here, probably generated by the precipitating auroral electrons, and this is auroral kilometric radiation propagating from the magnetosphere higher altitude range. And these are plasma waves, including BBELF, broadband, extremely low frequency plasma waves, probably associated with ion outflow in Dayside auroral cusp region. And in addition to these natural plasma waves, we can also see the resonance waves here, local resonance plasma waves here, and we can also see the artificial radio waves propagating from the ground can be also seen in this spectrogram. And this is the NEI and PWM data from several atmospheric sounding rocket experiments are archived and provided through the server at JAXA. And you can take a look at those data through this URL. So if you are interested in those data, please visit this URL. And we would like to move to the second topics. How does NEI measure the electron number density? In this talk, I have not yet explained how NEI can measure the electron number density. And in order to simplify, we would like to replace cylindrical metal probe to capacitor type probe in the plasma. And the current in the plasma is expressed as this equation. The we can see dielectric tensor of the plasma is here, and the elements of the tensor can be expressed by plasma frequency and cyclotron frequency, and they are dependent on the electron number density and magnetic field intensity. And current between the two probe plates probe plate is given as this equation by using the element of the dielectric tensor of the plasma. And the admittance of the capacitor in the plasma is given as by dividing current by current with voltage, and you can obtain the admittance of the capacitor. And by using the current in the plasma, we can obtain like this equation, and we can obtain this equation. And they are the same with the parallel circuit, admittance of the parallel circuit of C0 and Z1. And impedance Z1 is expressed as like this equation, and we can obtain this is equal to the impedance of the serial circuit of C1 and L1. And plasma sheath is formed around the probe like this, and act as a series capacitor CS. And so the probe can be expressed as this equivalent circuit composed of C0 and C1, L1, and CS. We can consider the probe extended in the plasma by using this equivalent current, equivalent circuit. And these plasma capacitance is measured by the capacitor bridge in the NEI. And this is probe capacitance as a function of frequency. The horizontal axis shows the frequency, and vertical axis shows capacitance of the probe extended in the plasma. And we can see maximum CP at frequency, maximum CP at this frequency. And this frequency depends on the capacitor of the sheath. This resonance is called sheath resonance. And you can see also minimum CP at frequency here. The frequency depends on the cyclotron frequency and plasma frequency. And cyclotron frequencies can be determined by the magnetic field model or observation by the magnetometer. We can determine cyclotron frequency. So by using upper hybrid resonance frequency, we can the frequency at CP minimum, and by using this frequency, you can determine plasma frequency, and by using plasma frequency, you can determine electron number density from this observation. And it is also important to adjust this capacitor circuit to be satisfy this equation in order to avoid shift of this resonance frequency. It is very important for developing impedance probe and final arrange of the development. In the final arrange of development, this adjustment is very important for in the calculation. Then we would like to move to the final topics, our plan for future missions. We are now preparing for the next ionospheric sounding rocket experiment in July 2024. The purpose of this experiment is 31046 sounding rocket experiment is the purpose of this experiment is detailed observation of day-side sporadic E layers in the summer ionosphere. Many scientific instruments will be installed on the rocket. Neutral wind velocity, ion velocity, electron number density, electron temperature, electric field and magnetic field, very many parameters can be obtained by using this large number of scientific instruments. And in verification of wind shear theory in C2 campaign, the ion velocity was not directly measured but estimated from neutral wind velocity and electric field. In this S31046 sounding rocket experiment, the theory will be verified in detail with more measured parameters. So we are now developing for the observation planned in the scheduled in the July in 2024 in the next year. And we have another plan of ionospheric plasma observations by low Earth orbit satellite in 2025. The main purpose of this LEO satellite mission is to perform the space experiment of the micro wireless power transmission between from LEO satellite to the ground and between LEO satellite and daughter cube satellite in the space. And since the experiment is performed in the ionosphere, intense microwave could affect the ionospheric plasma. And in order to evaluate the effect of intense microwave to the ionosphere, intense microwave to the ionospheric plasma, NEI and PWM is planned to be installed on this low Earth orbit satellite and 6U size cube satellite. And especially for installation of this cube satellite, some modification of the NEI design would be needed for downsizing. And the development of such downsized NEI is also performed in order to in order to perform the observation planned in the 2025. And this is a summary of this talk. Where NEI and PWM were used for observation of the electron number density and plasma waves in many ionospheric sounding rocket experiments. And NEI measures the capacitance of the probe in the plasma. And since the electron number density was determined on the basis of the frequency response of plasma permittivity, precise measurement of electron number density is possible by NEI. And we are planning to extend application of NEI and PWM from the ionospheric sounding rocket experiment to wider usage, such as small and cube satellite mission in future. And if you are interested in details on NEI and PWM and data from them, please feel free to contact us. Thank you for your attention.
Yeah, thank you so much, Professor.
Thank you.
Yeah, thank you so much for this very interesting talk. I think you have done very well. You know, I mean, using the NEI. And it seems that the impedance probe can give you a very accurate electron number density without the problem of a Lemieux probe. I mean, from Professor Oyama, he kept on warning us that Lemieux probe is not easy to do. I'm also very interested in the last part of your talk about the rocket experiment, yeah, with the mass spectrometer. You build a mass spectrometer also?
Kumamoto-san, we are talking.
Yeah.
Okay. I think they have also mass spectrometer, neutral mass spectrometer. But in my opinion, it's very difficult to measure mass spectrometer because around the height of 100 km, still background pressure is very, very high, 10 minus photo. Yeah. Then we might have a special preparation, like to have just to have the shield before the measurement, and after that we need to have a pumping, differential pumping. So I am afraid that you need a lot of work to measure neutral density. Okay, this is my comment.
Yeah, I mean, do you know who built this mass spectrometer?
Yes.
I mean, Tohoku or somebody else?
Oh, in ISAS.
Oh, ISAS.
Saito-san is doing.
All right.
Mass spectrometer.
Yeah, I mean, I know the neutral mass spectrometer.
Okay, you can contact, but I am very much afraid that their instrument might fail.
Yeah.
Very difficult.
And you also mentioned that Professor Kumamoto, you also mentioned the Ohisama mission, right?
Yeah, Ohisama. Yeah.
That's also very interesting.
Yeah, microwave wires power transmission experiment missions.
And
yeah.
And I don't understand because from this picture you have the satellite, the LEO satellite, and then you have a 5-meter boom, and then
stabilize.
And then you have the end of boom. You have a 6U CubeSat.
Yeah. I heard that this CubeSat has reaction foil, small reaction foil, and stabilize the altitude of the cube satellite.
And it's separate from the satellite, right? I mean, the LEO satellite and the CubeSat, they are separated from each other. Or they're attached.
The CubeSat has reaction foil, and by using reaction foil, the attitude of the cube satellite would be stabilized.
Okay. Yeah, this is very interesting. Any other questions from the audience? I mean, there are lot of material in this talk, and you could go back. You know, we will record it. We have recorded this talk video, and we put it on the web page, and you could go back and study it. And also that Professor Kumamoto has given his address, email address to us. And then you have questions. I think he welcomes you asking questions, and welcome you to use this data. So you can see that his
yeah. We have data archive, and some data can be provided by contact.
Right. And this project, this rocket project is from ISETS or from Tohoku. The rocket to be launched in July next year, is it from ISETS or from Tohoku?
From Kagoshima.
No.
Kagoshima Space Center.
Kumamoto-san, Professor Ips asking me whether this rocket is launched by ISAS or Tohoku. You understand?
Sorry. Sorry. This rocket was launched by the ISAS.
ISAS, okay.
Yeah, ISAS, by using facility of the JAXA ISAS Kagoshima Space Center.
So this ISAS rockets, very good. Okay, any questions? Oyama-san, you want to add something to this?
No, for the moment.
Yeah, and the audience, participants, do you have questions? You can ask, just raise your hand. And I mean, in future we will have a number of other lectures on instrumentation. I can make some advertisement. Professor Johnny Shea, retired professor from University of Arizona, and Professor Eberhard Mobius from New Hampshire. They have agreed to give talks, on instrumentation. And I also have just met Professor Stefano Levi in Singapore. And he has also agreed to give a lecture, on our lecture series. So in the coming months, we will have a number of very distinguished, excellent scientific talks. And I want to thank Professor Kumamoto again for giving us this very important, interesting talk today, and about the ionospheric measurements. It seems that after many years, there's still much to do with the ionosphere, the measurements. The sporadic E problems, are still very much, to be tested. It's interesting to see that. Yeah, and thank you so much. We will finish the session today, and hope to see you again next time. Thank you, everybody.
Thank you very much.
Thank you.